Okay, a graph is a collection of nodes and edges. And when I say graph, I'm talking about this kind of graph. I'm not talking about this kind where you have like X and Y axes. That is not what we're talking about today. Okay. So graph is made out of nodes. You can call these points or dots or vertices or whatever you want. Oftentimes the formal name is node, but it doesn't really matter that much. And it may or may not be connected by edges. So it's possible for me to add like a point K to this graph. So it's part of this graph. It just doesn't happen to be connected. Also, the location is non-specific. So I could move this point around and it wouldn't really matter where I put it. I can't move the rest of them around quite like that, but you can. So it doesn't really, there's not like a coordinate place where they are. And then edges are lines connecting nodes. They tend to represent some sort of connection. So maybe all of these nodes represent houses and these are roads in between those houses. Or maybe they're connections between people, right? Person C knows B and E directly, but does not know D, and nobody knows who person K is. Could be like that. Important that these do not have to be straight. Obviously, you can see some curves. Also, the length does not necessarily matter, right? Like the strength between A and B's connection is not necessarily more strong or less than the strength between B and F. Okay, the degree of a node references just the number of edges that are connected to it. So like in this case, M has 1, 2, 3, 4, 5. So M is degree 5. N here, this would be degree 3. And P would be degree 4. Literally, it's just the number of edges that are coming to it. You might notice this pink graph. This is what we would call a weighted graph, and this would be a non-weighted graph. And they represent the same thing. If you notice, there are 2 edges between M and N, and this is just the edge with the weight of 2 on it. Here there's 3 edges, and it's got a weight of 3. Here there's just 1 edge. It's got a weight of 1. So both the green and the pink are showing the same relationship. They're just slightly different in the way that they're shown on the page. And both of them can be represented by this adjacency table. This is literally as simple as, is M connected to whatever or here, right? M and N are connected by 2 edges, right? 1, 2, or the strength of 2. Notice that's kind of, oops, wrong thing that I used. There we go. That's kind of duplicated right here. There is some sort of duplication that's happening along this line, this reflection line here, but don't worry too much about that yet. Yeah, but this just represents the strength of the connections here. There was a question with respect to degrees. What happens when we have a loop? This is a loop, and it's just an edge that connects a node to itself. This happens a ton, no matter what you're doing. There's lots of reasons why you might need a loop. In this case, U has a degree of 2 just because there's like 1, 2 edges coming off of it. W has a degree of 2, and I'm going to argue that V has a degree of 4. I checked in with all my math teacher friends, and the general consensus was that 4 is the best answer, and you'll see a good reason for that in a moment or two. But one way to think about it is just like, if you zoom in real far here, how many edges are actually coming off of this? And since none of these are directed, we can just say 1, 2, 3, 4. I know there's just 1 edge here, but since it is connecting to V twice, we're going to count that as 2 connections. Okay, some more vocabulary here. A walk or a path is a continuous connection between nodes. It doesn't have to go through everything. It doesn't even have to go through most of them. You could start here and then just like walk. Cool, that is a walk. That's an example of a walk. You could also have a walk where you start here and you are done. That's it. It's just moving along one node. Just imagine, if you would, like a little person, if they were literally going to walk along these paths, what could they do? Any of those would be a walk. A cycle or a circuit is the same thing. It's just a walk that ends where it starts. So in this case, if you take your dude and let's say dude starts here, then walks around and walks and like, okay, cool. That right there would be a circuit. If you start, come around, and then you're done. You could also have a more elaborate circuit. It doesn't have to be that short, of course. You could maybe go like that. Cool. That right there would also be a circuit where your dude, come on, dude, there we go. Dude just ends up walking around and then they end up back where they started. A connected graph is one that looks like this, where all of the nodes are connected. Notice they don't all have to be connected to each other. That is what we would call a complete graph. D and G do not have to have a connection between them, but I can get from D to G. An unconnected graph then would be when you have like a lonely, at least one lonely point over here. Or if you had, you could also have, I could add it on here. You could have two separate kind of subgraphs that are happening here, where here is a graph, here's a graph. The whole thing is considered a single graph, but they're not connected to each other. A directed graph is a graph whose edges are directional, and that tends to be marked by arrows. So in this case, if I'm at M, I can't just walk right back to N because the arrow is going this way. So I could get to N if I went all the way around. If I was at O and I wanted to get to P, I'd have to go along this path, not that one, kind of thing. And directions actually introduce something called weak and strong connection. A weakly connected graph is a directional graph where at least one node is able to be reached, is not able, good gracious, you'd think I would have fixed that by now. Not able to be reached by a walk from any other node. In this case, the mu. If I started over here at sigma, I could get to phi, but I can't get to M because both of these are moving away from it. So this is what we call weakly connected. I can't go anywhere I want. Strongly connected, I can get anywhere I want. Now it might take me a while, right? To go, I can't go directly from J to I, but I can go through H and end up at I. This is a strongly connected graph. This one up here, also strongly connected. If I want to get to N and I am at M right now, I just have to go kind of around the way, or maybe like that to get there. And at long last, we are now at the Eulerian Walk, created by a dude named Euler. And this is basically a walk that covers each edge, and that's going to be super important, exactly one time. And I probably should have used my highlighter there. There we go. And this actually came about because of a very famous problem called the Bridges of Königsberg. This is Königsberg. We have all of this lovely land and islands, and they're connected by bridges. And the idea was people used to make a game of it, you know, before there were cell phones and stuff. Can I walk over all 7 bridges without having to double back and go over one of them twice? So can I go over all of them? And it turns out in this case, actually, I don't want to tell you the answer. You should figure it out yourself. If you were going to make this into a graph, here's a classic version of it. There's 2 connections here. There's 2 connections here. A connection here. Connection here. Do you see it? If this is kind of like your island in the center, you've got your 2 edges right there. See if you can figure it out. Pause the video, take a second, and then I'll explain. Here's what happens. This is not possible. And the reason it is not possible is because all of these have an odd degree, right? This edge has a degree of 3. This has a degree of 3. This has a degree of 5, and this has a degree of 3. Well, if you just think about any old edge, and it's got all sorts of things coming off of it, if I'm going to, let's say, start here, and then I'm going to go and do a whole bunch of stuff, and then maybe I come back here, and I leave again, and then I come back, it's the coming back and the leaving that matters, right? Because at some point, you're going to have to start at one of these edges. So let's say I start here. If I start, then I'm going to have to somehow come back and leave again because there's an odd number of edges here. So I either have to start, I can't just start and end here. I've got that extra one hanging off. Now, if you have 4 connections or 2 or 6 or any even number of connections, like right here, I could come in, go away, come back in, and leave again. That's perfectly reasonable. We don't really know what happened at this end or at that end, but I can get through there. I could also say that I started at an even place, right? I could start here, go away, come back, and end here. That's perfectly fine. I could end up doing that. So even numbers don't really matter. I could start there, I could end there, doesn't matter. But if it's odd, you have to either start or end there. And so in this case, I've got 4 places, but I only need to start and end twice. It leads us to this kind of strange rule. For an Eulerian walk, you can have at most 2 nodes with an odd degree, and you know your walk will start and end at those nodes. In this case, I've got 4 of them. It's never going to happen. Naturally, since we talked about edges last time, because I wanted to go over every bridge, now we're going to talk about nodes. And a Hamiltonian cycle, you could also do a walk, is simply a cycle where you visit every node exactly once. And since it is a cycle, you need to end where you started. So if I start here, there's lots of different ones that will work, but this is a fairly simple one. There, that is a Hamiltonian cycle. I left out some edges, but I visited every node and I ended where I started. This isn't quite as straightforward as the Eulerian walks as to whether or not it will or will not work, but you would know that if you had, so like if I deleted this edge, there's no way that a cycle is going to happen because I can't have a cycle when I've got something hanging out over here, because eventually I'll have to visit this edge or this node, and I can't go back and I can't end up where I started. I could do a walk, right? I could just go like, okay, cool, let's just visit all of those nodes, but I can't do a cycle. Okay, whole lot of information. Please let me know what questions you may or may not have.